Now we want to extend our understanding of Newton's laws to include curved motion. The simplest form of curved motion is motion in a circular path at a constant speed. This is what we refer to as uniform circular motion. Say you tie some mass to a string. If you swing this around, the string keeps the mass from flying off and it travels in a circle. Another example is the Earth revolving around the Sun. There is no string, but the force of gravity keeps the Earth tied to the Sun in a more or less circular path. If we go back to our discussion on acceleration, we found that an object can be traveling at a constant speed, but still be accelerating if it's changing direction. This refers back to Newton's first law that says that an object will remain at a uniform motion unless acted upon by an outside force. Say we have our ball being swung in a circle by a string. The velocity is constant, but since it's changing direction, there must be some acceleration. But in what direction? Think about what would happen if the ball were to break loose from the string. The ball would travel on in a direction tangent to the point where it was released at some velocity v. So we can actually represent the velocity at that release point with a vector in the direction the ball travels after its release. Since the ball does not travel off in some straight line, there must be an acceleration acting to change its direction. In turn, the ball must have been pulled by some force, in this case the string, from the path it wants to travel. Look at another point on the circle. When we see what direction the ball wants to travel and where it must be being pulled, we can see that the acceleration must be directed towards the center of the circle as well. The acceleration acts towards the center of the circle and is referred to as centripetal acceleration. So a couple things that need to be reiterated here. First, the magnitude of the velocity does not change. That is where the uniform part of our uniform circular motion comes in. Also, the velocity direction at any point along the circle will point in a direction tangent to that point. Second, the acceleration is coming from the change in direction only and points towards the center of the circle. So now we are interested in figuring out the magnitude of our centripetal acceleration. Here we have our object, whatever it is, traveling in its uniform circular motion. The particle moves from one position to another along the circular path. The magnitude of the velocity at the first position is v, and the magnitude at the second position is also v. The displacement between these 2 points can be represented by delta L. If you imagine a line drawn from the axis of rotation, which is the center of your circle, to the edge of your rotational motion, this is called the radius of curvature and is abbreviated as r. It's just the radius of your circle. As the particle moves along the circle, the radius of curvature forms an angle, theta, at the center between any 2 given points. Something to point out here, the radius of the circle is the same for both points 1 and 2. Also, since the velocity vector is drawn at a point tangent to the circle, the radius and the velocity vector form a right angle. So if we pull out these vectors and connect them as if they were at either point, we can compare the direction of the first velocity to the direction of the second velocity. If we were to close the other side, we get a triangle that shows us the change in velocity. Since all of our sides are similar to the vectors we would find on the original circle, the change in the angle of the radius of our circle corresponds to the velocity vectors, and the displacement along our circle corresponds to the change in velocity. So we have 2 isosceles triangles. If you remember from geometry, 2 isosceles triangles that have an angle of the same magnitude are similar triangles. So now we can compare these 2 triangles. The radius of our circle corresponds to the velocity vectors, and the displacement along our circle corresponds to the change in velocity. Now if we shrink our change in time and make it very small, this in turn is going to shrink our change in theta. In turn, our displacement is going to be smaller. As we do that, the line that represents our displacement is going to be more closely represented by the curve of our circle. So the distance our particle travels along the arc is going to be closer to the straight line distance between those 2 points. So for very small angles, we can say that the distance that we travel along the arc of our circle is equal to the displacement between those 2 points. We can quantify that and relate it back to our velocity by taking the velocity times the time. Now we have these 2 similar isosceles triangles, and if you remember from geometry, the ratio of the bases of the 2 similar triangles is proportional to the ratio of the sides of those 2 triangles. The base of our circle triangle is the displacement, which we have written as the velocity times the change in time. The base on our vector triangle represents the change in velocity. So the ratio of our bases is delta v over v delta t. The sides of our vector triangle are represented by the velocity at points 1 and 2. Since these are equal, we don't really need to distinguish. It's just the velocity of our particle as it moves around the circle. The sides of our circle triangle are the radius of the circle. So we can put those into our other side of the ratio. This gives us a relatively simple expression that relates the change in velocity over velocity times change in time to the velocity over the radius of the circle. Now look closely at that first term. We have change in velocity over change in time, which we know to be acceleration. We can move that v out of there, and then we can say that our centripetal acceleration is equal to the velocity squared divided by the radius of the circle. Okay, so how do you find the velocity of something moving in a circle? Since our something is moving in a circle, we can say that it is in orbit around the center, and that lets us refer to this velocity as the orbital velocity. You also probably know that the distance an object would travel in a circular orbit would be the circle's circumference. Circumference is determined using 2 pi r, where the r is the radius of the circle. Velocity is the same no matter what shape it takes on, so if we know the time it takes to complete one revolution, we can determine the velocity of the ball. We simply take the total distance traveled, 2 pi r, and divide it by the total time. So say we have a 150 kilogram ball at the end of a string that revolves in a horizontal circle with a radius of 0.6 meters. If the ball makes 2 revolutions in 1 second, what is its centripetal acceleration? Well, we're looking for centripetal acceleration. We have time, the radius of the circle, the mass, and the number of revolutions. But in our equation, we need to know velocity. Well, we can find velocity if we know our radius and our time. We know the radius, and it says that our time is 1 second. But that 1 second is the time it takes for the ball to travel through 2 revolutions. So the time it takes for the ball to move through 1 complete circumference would be half of that time, or half a second. So the orbital velocity of our ball is 7.54 meters per second. From there, it's pretty simple to substitute that into our velocity and radius and find a centripetal acceleration of 94.7 meters per second squared. So uniform circular motion describes an object moving in a circle at a constant velocity in terms of magnitude only. Okay, if it's moving in a circle, it's changing direction, so it does have an acceleration. We call that acceleration centripetal acceleration. The equation for centripetal acceleration is pretty simple. Velocity squared divided by the radius of your circle.